And what are the differences between the linear SVM and the non-linear SVM? Okay, so linear SVM is used for linearly separable data. That means where you can just draw a straight line and separate the data in two parts, okay, the two classes or two groups. So the equation is very easily represented with a W transposed X plus B, where W is the weight or the slope of the line, X is the input vector, and B is the bias. So this, see, it's just a equation of a straight line. And nonlinear SVM is a little bit different. Nonlinear SVM is used for data where it is not just linearly separable, like it looks like a circle, and in the middle will be like the negative or the minus instances, and around it will be the plus instances. So what we need to do, we have to project it in a higher dimensional plane, so that if it's in a 2-dimension it looks like that circle, in a 3-dimension it might look that the negative instances are above the positive instances, and there can be a plane between them to separate them. So that would be the hyperplane. Okay, so when the decision boundary is a nonlinear function, so then that is called a nonlinear SVM, and it maps the input data into a higher dimensional feature space using a kernel function. We can talk more about it later. It's not immediately important. And so using that higher dimension, as I said, in the 2-dimensional, if there are points which looks like a circle and mixed up, in a higher dimension, if we project it, we'll see that the negative instances are at this level, positive instances at this level, and there can be a plane between them. So that will be a hyperplane, and the equation here will be f of x equal to W transpose psi x plus b equal to 0, where psi x is here the feature vector, okay, in the higher dimension, and W is the weight vector, and b is the bias. Talk about a very important thing, which is the equation of the decision boundary and the vector W, which is perpendicular to the decision boundary. Let's see how it works. The decision boundaries equation, this is the decision boundary, the green one. I have drawn it as a, and the equation is Wx minus b equal to 0. Okay, so we have chosen it like that, and Wx minus b equal to 0 is nothing but an equation of a line like y equal to mx plus c, or y equal to wx plus c, where c is the intercept, and here we can represent c equal to minus b. Okay, so if you try to represent like that, and if y and c are 0, then the equation becomes nothing but w dot x equal to 0, right? So now if you write it in a vector form, it will be w dot product of x, there are two different vectors, equal to 0. So in a matrix form, as I've already shown earlier, that w transposed dot x equal to w1, w2 until the weight vectors. This is a row vector, and the x, which are the features, is the column vector. And if you remember, the dot product of two vectors are 0 is 0 when the one vector is perpendicular to the other, or they are orthogonal to each other. Okay, so now x is on the green line. Okay, x is on the green line, so w is definitely the one orthogonal to that green line. Now we have to see that the intercept is 0. Okay, c equal to 0 or b equal to 0, whatever you say. The intercept is 0. So when a line's equation intercept is 0, that means the line is passing through the origin. That's why I've drawn W through the origin, and then I'll extend that in that way so that it crosses the green line and it's a perpendicular to that. So you see also there's another important thing. If we have like two other points like xa and xb on that green line or the decision boundary, then the equations can follow this format and can be written at w times xa equal to 0 and w times xb equal to 0. Now I want to kind of subtract them. If we want to subtract these two equations and see like the distance between xa and xb, then I can get another vector, which is xa minus xb. It's a vector subtraction. Please understand, it's a vector subtraction. It's a dot product of w with the subtracted vector xa minus xb equal to 0. And what it brings, we'll talk about it. Same equation above, w times xa minus xb equal to 0. You see, this is a given that w times xa, w dot xa equal to 0 and w dot xb equal to 0. That means both this the lines, they pass through the origin also, because the intercepts are 0 as well. So you see in this picture, this is xa and this is xb. These are 2 points on the decision boundary, and the vector xa minus xb is nothing but this subtracted vector, okay, xa minus xb. So there is another way of doing that. I've drawn another picture here. So this is the hyperplane, the blue one, and then the black line is the perpendicular to the hyperplane, which is w. We have already shown how it is perpendicular. And then there are two more vectors, xa and xb, which are also from the origin, if you reach from the origin. And then the subtraction of xa minus xb is this vector, okay, xa minus xb. Now we can slide that vector and match it with the tail of the vector w, and we can see that because that vector is on the hyperplane, so they are orthogonal to each other, perpendicular to each other, and this property will be the most useful property. So for any vector, two vectors, to compare them, what we will do, we'll make a projection on the perpendicular to the hyperplane, that means on the w vector, and then match their length and see that which one is bigger or longer, and then based on that we'll make a decision to how to classify a particular point.